What if I told you the greatest journey in human history is about to get a sequel? For nearly 50 years, two probes, relics of the 1970s, have been our only eyes and ears in the vast dark ocean between the stars. But their time is running out. Now scientists are designing a successor, a true interstellar explorer built for the 21st century, powered by next-generation systems and guided by artificial intelligence. This is the story of humanity's next great leap into the cosmos, so let's explore this together. The original Voyager achievement. Ever wonder how two probes from the 1970s became the greatest explorers in human history? The answer is a mix of brilliant engineering and perfect timing. Managed by the Jet Propulsion Laboratory, Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare planetary alignment that happens only once every 175 years. This grand tour alignment allowed them to use gravity assists, slingshotting from one giant planet to the next. Under the guidance of scientists like the legendary project scientist Ed Stone, who served for 50 years, the discoveries were staggering. We saw active volcanoes spewing sulfur on Jupiter's moon Io, confirming 9 active eruptions and making it the most geologically active object in the solar system. We discovered the icy geysers of Neptune's moon Triton, a world so cold it spews nitrogen frost. These missions completely rewrote planetary science textbooks, all accomplished with custom-built computers that had just 69.63 kilobytes of memory, less than 1/1,000,000th of a single photo taken by a modern smartphone. They transformed our view of the outer planets from fuzzy telescope images into a detailed family portrait, revealing worlds more dynamic and complex than anyone had ever imagined. It was a mission of firsts, providing the data that forms the foundation of modern planetary science. A journey into interstellar space. So what happens after you complete a grand tour of the outer planets? You keep going, farther and faster into the unknown. After their primary missions ended in 1989, the Voyagers began the Voyager Interstellar mission. Their new objective was to reach the edge of the heliosphere, the vast magnetic bubble inflated by our sun's solar wind that shields the planets from about 75% of galactic radiation. For years they traveled toward this boundary. Then on August 25, 2012, Voyager 1 made history at a distance of 121 astronomical units, or 121 times the distance from Earth to the Sun. It crossed the heliopause, the final frontier of our solar system, and entered interstellar space. Stamatios Tom Crimigis, a lead investigator, confirmed the data was undeniable. Voyager 2, on a different trajectory, followed suit on November 5, 2018, at about 119 AU. Now, Voyager 1 is over 163 AU away, the most distant human-made object in existence. For the first time, we were getting direct measurements of the interstellar medium, data sent from a place no probe was ever truly built to explore. Current limitations of the Voyagers. Here's the fundamental problem. The Voyagers are technological marvels, but they are also relics. They were designed for the powerful environments of planets, not the subtle nuances of interstellar space. Their magnetometers, for example, were built to measure the powerful magnetic fields of gas giants, not the faint, tenuous fields between the stars. Their cosmic ray subsystem can detect energetic particles, but it lacks the sophistication to distinguish between different heavy elements with the precision a modern instrument could, which is critical for understanding the origin of these rays. Furthermore, their power source, which uses heat from decaying plutonium-238, is fading. The initial 470 watts of power has dwindled, losing about 4 watts of electrical power each year. To conserve what little energy remains, engineers on the ground are in a constant race against time, making difficult choices about which instruments to sacrifice next. Their data trickles home to the Deep Space Network at a mere 160 bits per second, meaning it would take over a week to send a single low-resolution photo. The signal is now so faint, billions of times weaker than a watch battery, that it requires the world's most sensitive radio antennas just to hear it. The case for Voyager 3. With the original Voyagers fading, the question isn't just about continuing their legacy, it's about launching a revolution in interstellar science. The scientific community, including visionaries like Ralph McNutt Jr. from the Johns Hopkins Applied Physics Laboratory, isn't talking about a simple sequel. They are proposing a dedicated interstellar probe. This concept, often nicknamed Voyager 3, would be a machine designed from the ground up for a 50-year mission to explore the interstellar medium. It would carry a suite of modern instruments specifically built to analyze the space between stars with a precision the Voyagers could only dream of. The goal is ambitious, to travel 1,000 astronomical units from the Sun, which is more than 6 times farther than Voyager 1 has traveled in nearly 5 decades. This isn't about nostalgia for the Voyager name, it's about a critical scientific imperative. The Voyagers proved we could touch the stars, but they left us with more questions than answers. A new probe would be our tool to finally understand our place in the cosmic neighborhood. Advanced technology capabilities. So what kind of upgrade would a modern interstellar probe get? Let me explain. Compared to the Voyager's 1970s technology, a new probe would be a revolutionary leap. Instead of limited sensors, it would carry a suite of advanced instruments, a plasma spectrometer, energetic particle detectors, magnetometers, and a dust counter, all with at least 100 times the resolution of the Voyager's equipment. Power would come from a next-generation RTG, designed for longevity and providing enough power to run a full suite of instruments for a century. But the real game-changer would be its brain, AI-powered autonomous systems. This would allow it to make its own decisions, acting like a true robotic field scientist. It could prioritize data, compressing less important information to save bandwidth for groundbreaking discoveries, and even react to unforeseen events without waiting for the 3-day round-trip communication with Earth. To achieve its speed, the mission would launch on the most powerful rocket available, like NASA's SLS Block 2, and perform a powered Jupiter gravity assist, using both Jupiter's gravity and an onboard engine to achieve velocities previously thought impossible for a long-duration science mission. The interstellar medium mystery. Why is it so critical to study the space between the stars? Because our solar system is not an island. It's a ship sailing through the interstellar medium, and the heliosphere is our hull. For years, we thought this protective bubble was shaped like a comet, with a long tail stretching behind it. But the data from the Voyagers, combined with models from astrophysicists like Merav Ofer of Boston University, suggests something far stranger. Her models indicate the heliosphere might be a deflated croissant or have 2 distinct jets, a shape no one predicted. The truth is, we don't know for sure because we only have 2 data points from the Voyagers. A dedicated interstellar probe with modern plasma and magnetic field sensors could finally map its true structure. It would directly measure the density of the local interstellar cloud our Sun is passing through, about 0.1 atoms per cubic centimeter, and chart the strength of the interstellar magnetic field. Understanding this interaction is fundamental to knowing our place in the galaxy and the nature of astrospheres around other stars. Scientific objectives and research goals. Let's get specific. What questions would a mission like the interstellar probe finally answer? First, it would explore the unshocked interstellar medium, the pristine galactic material our Sun is moving through. This means getting a baseline chemical inventory of our galactic neighborhood, the very stuff from which future stars and planets will form. Second, it would map the structure of our heliosphere in high definition, crossing key boundaries like the termination shock and heliosheath with far more advanced instruments. It would finally solve the mystery of its shape and reveal the physics of its interaction with the galaxy. Finally, the mission would journey to a target of 1,000 astronomical units from the Sun. As physicist Ralph McNutt from the APL team emphasizes, getting to this distance would allow us to look back and view our solar system as a complete astrosphere for the first time. From this vantage point, it could even detect the faint extragalactic background light without interference from dust in our solar system, opening a new window for cosmology and studying the universe's first light. It would be a multi-purpose observatory unlike any other. Practical applications for future missions. This isn't just about pure science, it's about laying the foundation for humanity's future in space. A modern interstellar probe would be a crucial pathfinder, charting the hazards of deep space. Its most important practical application would be creating the first detailed map of the radiation environment beyond our heliosphere. We know from Voyager data that the flux of high-energy galactic cosmic rays is roughly 3 times higher outside the heliosphere. These particles can damage electronics and pose a significant threat to biological life. A new probe would measure this radiation with unprecedented accuracy, providing the essential data engineers need to design shielding for future robotic and eventually human interstellar missions. Understanding the plasma turbulence and magnetic field orientation is also critical for developing safe navigation strategies. Just as early sailors needed charts of ocean currents and reefs, future interstellar explorers will need a map of the interstellar medium. This mission would create that first map, making the next steps in exploration possible. Cultural significance and golden record 2.0. What message would you send to represent all of humanity on a journey that will outlast everyone alive today? In 1977, Carl Sagan's committee assembled the Golden Records. An interstellar probe would carry on this legacy, but a Golden Record 2.0 wouldn't be a physical disc. John Lomberg, the artist who designed the original record's cover, has proposed a digital successor. This new archive could hold petabytes of data, the entire human genome, vast libraries of art and science, and perhaps even messages from the public. The new message would have to reflect our more globalized, digitally connected, and perhaps more self-aware civilization. The very act of creating it forces us to reflect on our collective identity and what we would want to say about ourselves to the cosmos. How do you represent humanity's flaws alongside its triumphs? Who gets to decide? This probe and its message will travel through the galaxy for millions of years, long after Earth has changed beyond recognition. It serves a dual purpose, a scientific instrument pushing the frontier of knowledge, and a cultural artifact carrying the story of humanity to the stars, a true monument to our civilization. Timing and opportunity. Here's why this conversation is happening right now. The original Voyager's Grand Tour was a once-in-a-lifetime opportunity. To achieve the immense speeds needed for a true interstellar mission in a reasonable time frame, we need a similar advantage. As identified by Ralph McNutt and the APL team, a powerful launch window opens in the 2030s. A launch in 2036, using a powerful rocket and a Jupiter gravity assist, would provide the optimal trajectory to reach the target speed of 20 astronomical units per year. Missing this window would mean waiting until the next alignment in the late 2040s, a significant delay for a mission that is already decades in the making. The technology needed for the core mission is largely ready or in advanced development. This isn't a far-off dream, it's an achievable plan with a clear timeline. The Voyagers have been our scouts, but their journey is nearing its end. If we want to build on their legacy rather than letting it fade into silence, the time to commit is now. The cosmos is waiting, and the launch window is opening. An interstellar probe wouldn't just be repeating the past, it would be a quantum leap forward. It would push deeper, answer fundamental questions about our place in the cosmos, and test the technologies needed for future missions to the stars. The first Voyagers were our first messengers to the galaxy, carrying a hopeful greeting from a small, distant world. This new probe could be our new voice, our new eyes, and our first true step beyond the sun's embrace. Are we ready to take that step? Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Stellar Tech.